Hi, it's time for another math. Easy. So we're going to discuss further into antiderivatives and basically look at the third part of the example series. And now I'm going to show some graphing and directional fields to discuss what these are. Basically, antiderivatives is, it's just a integral. You could think of that of a function here, and I showed before what it was. You could click on the video links below to see my recap on this and what antiderivatives are. Okay, so now let's just dive into the examples here. Basic example 1 says if you're given a function here, this is if, for example, just experimental data on this or whatnot, function f, we'll just call this f of x here, and then graph the antiderivative f here given that the antiderivative at x equals 0 is 2. Basically, remember, antiderivative is just, the derivative of it is just equals to f of x. So from this we could use what I've learned in what I showed before in how to graph like local max, minimum, inflection points and whatnot, on how to basically go backwards and graph what the antiderivative is if we're given this one. It's pretty easy. Now we'll just start by making a little y-axis here. Okay, so now we're just going to look at what we're given here. Basically f of 0 is 2, so if this is the f of x, we'll just graph it on this here. So this will be the antiderivative at 2, so this will be 2 here. And now we can see from this one, because remember this is a derivative of it, this is negative from here to here, this is less than 0. So because it's below the axis here, so if it's less than 0, then this just means that the antiderivative is decreasing. So it would be decreasing here, and we look at these 2 points here at 1 and 2 is when the derivative is 0. So this just means you're going to have horizontal slopes here. So if it's decreasing and then at 1 here, 1 and 3. So this one here, we're going to have a horizontal slope. So then we could just draw this part here. So it will go like this. So it's horizontal here, and then now it's increasing. So now it's greater than 0. If it's greater than 0, then this just means it's increasing here by the decreasing test. So now it's going to be increasing here. And then when you look at this point here, this is considered an inflection point, because here the derivative of this function, so if we go f prime of x, this is greater than 0, and then it decreases here to f prime of x less than 0. So then it's increasing, then decreasing, and then this is, remember, this is the derivative of this one is equal to the second derivative. The second derivative of the antiderivative is equal to the derivative of this one. So then if it's increasing, decreasing, this is basically an inflection point here, and also here as well. This one is decreasing and then increasing here. So we're going to have 2 inflection points here. So that's at 2 and 4. And remember, inflection points changes the concavity. So this will be 2, and then we'll have one at 4 here. So what this means is, so now at this point we know it's increasing, so it's concaving up in this case. That's because this is greater than 0 here. The derivative is greater than 0, so it's concaving up all the way. Yeah, it's concaving up, and then there's an inflection point right here, so it starts concaving down. And then concaving down here, and then the slope, remember, at x equals 3 is 0. So we're going to have a 0 slope here, or horizontal slope, and then it starts concaving down. Yeah, this whole thing is concaving down. This is concaving up, and then inflection point concaving down. This is at 2, and then it's concaving down, and then as you can see here, there's a inflection point at x equals 4. So this one's going to be inflection somewhere across here. So this is concaving down, and then it starts concaving up at this point here, and it's concaving up, and now this is approaching 0. And so what this means is that it's always going to be decreasing, because it's always less than 0 here. Just the derivative, or the f of x, always less than 0. And the concavity never changes again. So it's always going to be concaving up while decreasing. So it's going to keep going like this to infinity. Yeah, so basically, yeah, just using what we know from our calculus rules and whatnot, we get our antiderivative f of x here. So we get this one here. Now I'll show you an example using directional fields. For this one's going to be a bit more accurate drawing of this. Okay, so now if we're given this example here, example 2, graph, basically if we're given f of x is equal to, well, square root 1 plus x3 minus x, graph f of x with antiderivative at, if f of negative 1 is equal to 0 here. So what we could do is basically find the antiderivative of this, but this one's really complex here. You could try to think of it all day, you're not going to find it, and if you plug it into Wolfram Alpha, yeah, like I did right here. So if you just plug in the first part of the square root 1 plus x3 here, as you can see, it tells you the antiderivative or the integral here, and this is just this whole thing, x4 whatever this stuff is, and then f of sine. I don't you know what this all this stuff is. So you're gonna have something just ridiculous like this big. So this is that's just too hard to graph. Or you could also do what we did in example 1 here and basically graph this function here and then find the antiderivative of it. But now we're going to do something just a bit more accurate. We're going to use directional field. And what directional fields are just basically just drawing tangent lines of the derivative or of f of x, just a bunch of them at many different x values. So I'll just illustrate that here. So if this is the xy axis here, let's plug in this is -1 here. Let's just graph from -1 and greater than it, because this is what we're given here. So basically f of -1, this one, we'll just write that down here, f of -1, this one's just equal to, if we plug this in, we're going to get 1 plus -1 cubed, which is just going to be -1, because it's anything cubed, even if it's negative, it stays negative here. So we're going to get 1 plus, well, -1 cubed, so this is going to be 1 plus, 1 negative 1, 1 minus 1, this is going to be 0, and then minus x, which is just -1, so this just equals to 1. Yeah, so that's just going to be equal to 1 here. So what this says is that the derivative at x equals to 1 is going to be 1 here. So we just draw a tangent line or a directional field, just a bunch of them like this. Let's just assume this is roughly 1. It's a bad drawing, but anyways. So we're just going to do stuff like this, and then you're going to draw it whatever you want. So you just draw in a straight line, a vertical line at this x value. And now we plug in, let's say for x is 0. At x equals to 0. So I'll just write it down here, so it'll be a bit neater. So now we're going to get 1 plus 0 minus 1. No, I mean 0 is 1 minus 0. This is going to be just 1. So this one at this point here at x equals 0 is going to have the same slope. So we just draw the same stuff across here. So we just draw roughly a slope of 1 or tangent line across. It was centered at whatever the x value is. So now if we look at f of 1 here, this is just going to be 1 plus 1, or square root 1 plus 1 cubed, which is just 1 minus 1. Now we're going to get a square root 2 minus 1 here, and this one is, this is something like, we'll just plug that in. What is square root 2? It's less than 2, so square root 2 is equal, 1.4, let's just go minus 1. So that's 0.41 and 1 not. So then that is, the slope is a bit less than less than 1 here. So now we're gonna have a more horizontal slope at this one is x equals to 1 here. So it's a bit more horizontal. We'll just draw it a bit more horizontal than these, and so on. So we just keep doing something like this here, and then also for, let's go with 2. Yeah, with the 2 here, if you just plug this in here, f of 2, this is 1 plus 2 cubed. This is gonna be, well, 8. 8 plus 1 is 9, so we're going to have square root 9 minus 2, which equals 3 minus 2. And this just equals to 1 again. So now, as you can see here, this is more horizontal, and then it starts becoming more more vertical again. The slope is 1, similar to these ones here. Yeah, this is a bit, just pretend these are all similar. But anyway, so then if we do this one more one, so if we plug in the f of 3 here, so now we're going to have 1 plus 3 cube, this is 27, plus 1 is 28, so this is going to be square root 28 minus 3. Now this one is going to be, well, we'll just say it's bigger than 1 here, so it's a pretty big slope in this case here. So it's, because it's square root 28, that should be something like, I don't know what is 4 squared 16, so 5 squared is 25, so it's greater than 5, so 5 point something. So it should be a pretty big slope here. So at 3, we're going to have a pretty vertical slope in this case. So it's going to be something like this. And also, you could be more accurate, you could pick the, let's say, negative 1.5 and so on, and or 0.5 and stuff here. So we're going to have a bunch of these directional fields, and we just have to follow the direction to graph our antiderivative. Now we're going to pick, let's say, this point, f of -1 equals 0. So we know that it starts off here. So now we just draw it following these directional curves. So if, so you should have some stuff in here, but basically it'll be something like this here. It will go up. Yeah, so it's just going to be something like this then. yeah, so that's how our antiderivative should look like. Basically, you would follow whatever the curves are. Initially, this is slope of 1, and this one, I think it's going to be, yeah, this one is more sloped in this case, and then it starts curving down because this at this point here, it's less than 1 here at f of 1. So it's less than 1, so it curves down here, and then it curves back up because these slopes are bigger, or much higher. So yeah, that's what basically directional fields are. And if you had some powerful calculator or Excel sheet, you could probably do this more accurately. But basically, yeah, that's what it is. And this would just be f of x here. So this one you could, it's as opposed to this one, which was just basically just guess where it is, guess where it would stop here. But yeah, this is, you could also do this one. Hopefully you learn from these methods of graphing. But basically, yeah, you can download these notes like always in the Dropbox link below, and hopefully you learned, and stay tuned for another math easy solution.